In this video, we are going to look at a topic on measuring computational complexity. Okay, so we know that when we want to compute a problem or write a program and execute that program on a computer, because we are concerned with how soon we can get a result and how much memory do we need in order to carry out that computation. So that is really a resources that we have to compute a problem, right? So that's time and space. So these are computing resources. Hence, in order to measure computational complexity, we are going to look at models to analyze the time and space a computation would need to take. So it is different from traditional study or traditional approach to studying computability, because computability only concerns whether a problem can be computed by a Turing machine that on any input eventually halts. Resources there is no object, namely it doesn't care how long and how much space is needed. However, for all practical purposes, we want to know how long and how much space needed to carry out a computation. So then, again, how to measure time and space complexity. So this is what we are really concerned most as a computer scientist. Okay, so now let's look at time-bounded computability. So let M be a deterministic Turing machine. So as we know, we can view a Turing machine, a deterministic Turing machine, as a program. Okay, so for a computer, right? So that is a program that halts on all inputs. Okay, so this is a program, so we know that it's a program or any input, it will halt. Then the running time or time complexity of this program or this Turing machine is the function f, which maps an integer to an integer. In other words, we takes the size of the input and measure the number of steps it takes in order to produce a result. And that result, okay, so is the number of steps. Okay. So we want to measure, okay, for that result. So that is f, so this is a time complexity, where f of n is the maximum number of steps that m uses on any input of length n to produce a result. If f of n is the running time of m, we say that m runs in time f of n, and that m is an f of n time Turing machine, okay, or a program, or in general, an algorithm, because the program implements an algorithm. Customarily, we use n to represent the length of the input or the size of the input if you have multiple parameters in your input. So you measure the size of each parameter and then you add them up, which will be the size of your input. For instance, you must have already learned sorting algorithms in your computing 1 or computing 2. So in that, for instance, insertion sort, the running time of insertion sort is n squared, which takes which takes a number of numbers as input and produces an output which have these numbers in a sorted order, either increasing or decreasing. In particular, we are going to investigate a class of problems that widely exist in practice in almost every area involving computing, namely problems whose solutions are quick and easy to verify, but hard to find. Okay, so those are the problems that we are most interested in from this, computational complexity point of view. Finding an efficient algorithm to solve a problem is the subject of algorithms that you're going to learn in algorithm class, algorithm and analysis, algorithm design and analysis class. Here we are going to look at from using the notion of Turing machines to look at what would be considered efficient and what would be considered hard computationally. Okay. So in order to describe this computational complexity measure, we will need to use the following two notations, the big O and small o notations, because what we are measuring in this case is worst case running time asymptotically. So then we can use big O and small o to have a cleaner representation of this complexity measure. So here are a bunch of definitions. Let f and g be functions. So we think of it as time complexity function. Likewise, we can also consider it as space complexity. So instead of measuring steps, you're measuring the number of cells needed to carry out a given computation. So here are just the f and g be functions from integers to real numbers. Okay, so these functions, you can think of them as taking the size of the inputs, so which would be integers, and the output now is just positive real numbers to define big O and small o. Okay, so we say that f of n is equal to big O of g of n if positive integers c and n0 exist, such that for every integer n greater than or equal to n0, f of n is less than or equal to c times g of n. Okay, so this means that from certain point on, okay, so you have these inequalities hold. So when this happens, then we are going to write, when this happens, we say that g of n is an upper bound for f of n, or more precisely, that g of n is an asymptotic upper bound for f of n, to emphasize that we are suppressing constant factors. Okay, so now let's look at small o notation. So again, the f and g be functions from n to positive reals. Then we say that f of n is small o of g of n if you take the ratio f of n over g of n, which goes to 0 when n goes to infinity. Okay, so in other words, f of n is it's much smaller than g of n when you take the limit this ratio of f of n over g of n goes to 0. Okay, so that means that f of n is equal to small o of g of n. Then it means that for any real number c greater than 0, there is a number n0 exists such that for all n greater than or equal to n0, f of n is less than c times g of n. This is now, again, this is c is for any. So usually we are so it is customary to write epsilon as the c, particularly in calculus, right? So calculus usually means any number, positive number that's very, very small. Okay, but for any of these, okay, so that's how we use to define limit. Okay, now the following are some examples of this small o and big O. Okay, so the case root of n, which we can also write it n to the k minus 1, has the following relation. So if k is greater than 1, okay, then it is equal to small o of n, because when k is greater than 1, 1 over k is less than 1, so n to the 1 over k over n will goes to 0 when n goes to infinite. And then if k is between 0 and 1, okay, so this is just a so this just means that it is a normal polynomial, because when k is less than or equal to 1 greater than 0, this is going to be greater than 1, but then it is less than. So if you take a limit, so this also goes to 0 and n goes to infinite. So that's why that n to the 1 over k's power is equal to small o of 2 to the n. And if k is less than 0, that means that it is a negative number. So 1 over k is a negative number. Then if you put 1 over, because this is a negative, so that means that you have a positive amount there. Take the absolute value. So of course, this goes to 0 when n goes to infinity. So that's what we have here. So then you may ask, what happens if k is equal to 0? Of course, it's not defined, so you cannot have a 0 divisor. Okay. Now, likewise, we can have n is equal to small o of n log n, right? Because it's n over n log n, so this n canceled, so it still goes to 0. So likewise, it's equal to n, you can log as many times as you want. It's still true. Okay. So this you can log them as many times as you want. All right. So then so n log n is a small o of n squared, because as we said, so if you put n log n over n squared is equal to log n over n. So this goes to 0 when n goes to infinity. Okay, so that we done that, done this, done that, done that. Okay, so now let's look at n squared. So n squared is small o of n to the 2.1, or any number, as long as, so no matter how small it is, as long as epsilon is greater than 0. And we always have this goes to 0 when n goes to infinity. Okay, so we've done that. So now let's look at this. So we have n squared plus n to the 1.8 plus n log n. So now here's the beauty of using big O or small o notation, because we just need to look at the dominant factor. So in this case, n squared is greater than n to the 1.8 is greater than n log n. So that is simply big O of n squared, because n squared plus n to this plus n log n is less than n squared plus n squared plus n squared. That's 3n squared plus that is just big O of n squared. Okay, so and then we look at this form. So n to the 1 million plus 2 to the 100n. So you look at the domino factor when asymptotic dominance, okay? So when n goes to infinity, we know that this is the dominance, okay? So that means that n, it's 1 million plus 2 to the, well, even 0.n, okay? It is still, this is still the dominant factor when n goes to infinity. So this is 2 to the 0, n. Of course, we can use a big O to replace it, because the big O is just constant. Big O of 1, just a constant. Of course, 0.1 is big O of 1. And how small, as long as it's constant. So likewise, we can look at 100 to the nth power. So again, it's dominated by 2 to the n. So there's one thing that I think you ought to get very familiar with is n. So any n, oops. So any n, it is equal to 2 to the log n. So that means then 100n, 100nth power is equal to 2 to the log 100 to the nth power, so which is n log 100. But log 100 is a constant, so this is big O of n. Right? So that's what we have here. Similarly, you look at this, and you look at the dominant factor. So of course, n squared dominance n log n, so this is the dominant factor. So that's why we have this. So there are many such things. So using big O notation and small O notation, you just need to look at the dominant factor. All right. Okay, now let's define time complexity class. Again, we use Turing machines. So let T be a function. So we use small t, so implicitly we meant that this t is a time function. It's a function to measure time, okay, the number of steps. Okay, so it's a function from n to positive reals. So we define the time complexity class, time of t of n, to be the collection of all languages that are decidable by a Turing machine that runs in big O of t of n steps. Okay, so that's what this means. So now we have the following theorem that t of n be a function where t of n is greater than or equal to n. So assumably, we need to read off the whatever input you have, so because that at least takes the size of the input steps that you can read it off, because you can only read one symbol at a time using a Turing machine. So that's why we assume this is true. Then every t of n time multi-tape Turing machine has an equivalent big O of t square of n times single tape Turing machines. Because so the proof of this result is pretty straightforward, because what we need to do is to use a, let's say you have k tape. So this is a one-way unbounded in one direction. So assuming this is, you have a k tape Turing machine and you have a finite control. Right. Okay, so this is think of that as a program. Your tape is your input and output I/O plus a working memory. Right? To store intermediate results, to hold intermediate parameters, that kind of things. So now, how can we come up with a single tape, one-sided single tape? To simulate this, now again, the runtime of this is every, so this is, so it's a multiple tape. Say this is a K tape, the runtime is T of n. Okay, so how to big O. So let's put a big O bigger. Make it bigger. Okay. Now, how do we use a single tape to do it? So, of course, I can put the content here. And put the content here. All right. And then we put the content, the second tape. And then this is the first tape, second tape, and the case tape. Okay. Put it here. Okay, so now how do I do one step? All right. So remember that how long this is going to be for each portion of the tape. Now remember, it takes t of n time to stop for. So that means that the t of n, so for each tape, the memory, so the number of cells you're going to use will be less than T of n because you need, so the runtime needs to read these tape symbols. Okay, anything that's useful to carry out this computation will be the content that you need to put in here. So that is bounded above by T of n. So now for one move here, for one move of the multiple of the K-tape Turing machine, you are going to do, so this is T of n steps. You just move, right? So you look at how each of these is going to change, get this configuration. So you change that and then you move here, you move here. So that means for each move on the left, you're going to need K times T of n with a big O, many different moves to simulate that move. Okay, but then there's the total runtime of this K-tape Turing machine takes T of n. So then you use one tape, so that is K times T of n times T of n. So that is big O. Okay, so this is a big O. So that's kt of n times t of n, but k is a constant relative to n. So this is just big O of t squared of n. So that means that within polynomial, right, from t to t squared, it's within a polynomial that the power of a single tape is the same as the power of multiple tapes. Okay, so this is this theorem says. So now let's look at non-deterministic Turing machines. We can similarly define non-deterministic time for non-deterministic Turing machine. So for convenience, so let n be a non-deterministic time Turing machine that is a decider, because what we are interested in is anything that is computable, that in our case is solvable, in our case it's decidable, when we don't worry about time bound. Okay, so let n be a non-deterministic Turing machine that is a decider. Then we define the running time of this non-deterministic Turing machine, n, as a function f from n to n, okay, from integer to integer, from the size to the number of steps, where f of n is the maximum number of steps that n uses on any branch of its computation on any input of length n. Okay, so it's a decidable, so that means it will hold, it will eventually hold. Then how do we define its computation? I'm sorry, it's time, so what we do now is done non-deterministic. So you're from the initial configuration, right? So usually this first configuration is Q0x, which is your input string, and Q0 is your start state. And then let's say you have two possible choices to go to the next state and either change the symbol and either move left or move right. So likewise, from here you get three choices, So that means that we are going to have lots of branches, exponentially many branches, and some of them shorter, some of them longer, right? When every one of those will hold because it is a decidable, it's a decider. So the longest one, okay, so the longest of this is simply the time complexity of this Turing machine. Okay, so that's what that is. Okay, so now it's interesting to look at the relation between deterministic time and non-deterministic time. Non-deterministic time is not intended to correspond to any real-world computation. Rather, it is a useful mathematical concept that captures the complexity of an important class of computational problems. In other words, that is the question of P versus NP. Well, that's the problem of P versus NP that we're going to talk about in greater details, in great details, not just greater, in great details later. So the relationship between deterministic time and non-deterministic time is the following. So this is a theorem. So let T of n be a function where T of n is greater than or equal to n, then every T of n time non-deterministic single tape Turing machine has an equivalent to the big O of T of n time deterministic single tape Turing machine. Okay, because so if we move back to the previous slide, then we know that you have to look at all possible paths in a non-deterministic computation, and the number of or possible path, if each path is at most T of n in length, then it is 2 to the, it would be a constant, right? So let me start a whiteboard. Let me start a whiteboard here. So we have a n time non-deterministic time T of n. So what that means here is that on your initial configuration, so you may have lots and lots of paths, some of them shorter, some of them longer. So, and the depth here is T of n, okay? So then we can, for the sake of argument, we can think of all paths is exactly the same length, T of n. Now then, how many such paths there exist? So then we assume that because m is given, so on any given state, the number of states, the number of choices you can move to the following state is bounded above by a constant. So because this m is finite, so we just let d be the maximal degrees or the maximum number of states each state will depend, can choose from, right, for as its next state. So then the number of paths, it will take some shorter, some longer, but just take it as, so each of them is the same height, then we know that it is the maximum number of paths than any of the possible paths we talk about. So this is less than or equal to d to the t of n. Okay, but then d to the d of n is, now remember, as we said earlier, so this is single bound, this is one number, so this is equal to 2 to the log d t of n. So that means 2 to the t of n times log d. So log d is a constant because what you are given here, when m is given, it is a constant. So we can simply write it as 2 to the big O of t of n. So this is a d time. So if your n time is d of n, then your d time is 2 to the big O of t of n. Okay, so that is the end of this video.